Hiya guys, right? So 2357 or 1605 learners, it's the same course. 2357 City and Guilds, 1605 is the EAL. And we're gonna have a chat about the faults tonight. This is a nightmare, it's a minefield, everyone hates it, including me. So we're gonna go through what's required and maybe give you some examples of how we can help you sort this out and get this done, guys. All right. So let's crack on then. And I've made a little presentation for us. So 2357, 1605 faults, ball ache fixed. All right, so I'm going to do my best to try and clarify some of the points, some of the horrible things that we have to go through in these MVQs and try and make it a little bit easier for you guys, okay? So, what faults do we have to get? Faults you must show. Essential criteria. There's no way out of it, okay? 2357 and 1605 have a list of criteria we have to hit, and we're going to hit it. And if you don't hit it, you're not getting a qualification. That is the end of the chat, okay? So the first one then, we've got loss of supply to find. We've got overload, short circuit or earth fault, transient voltage, loss of line, incorrect phase rotation, high resistance joints and component faults. They are all the faults that you have to find and fix and show evidence of no matter what, okay? However, we can discuss the following faults because they're non-common. So there are some faults they've said to us, we're not likely to encounter them, so we just need to show knowledge of them. So what are they then? So the first one is transient voltage. What is a transient voltage? The transient over voltage are very short durations, increases in voltage, measured between two conductors or between a conductor and ground. In a nutshell, guys, a transient voltage is a short, unwanted spike in voltage. It's not a surge. Don't get confused between a voltage surge and a transient voltage. Transient means move, right? The example I'm going to give you for a transient voltage that we could talk about is imagine a dark room with a white plastic light switch, okay, that's got a broken rocker. And when you press it, it gives off a little, and you see a little blue flash. That little blue flash is a transient voltage. Could be something like a voltage off a lightning strike, big, huge one. But that, in a sense, that's a transient voltage. As long as you understand that and you relay that to me, then we can just have that discussion. You can tell me that and job done, right? The next one is going to be overload. Okay, so we're not always going to encounter overload. Remember, overloads are detected by the MCB device, right? Not the RCD. That's short circuit and earth fault, which we're going to go on to later. So an MCB is 32 amp, 16 amp, 6 amp MCB will be your overload protection. It describes a moderate and gradual rise in the value of current over a relatively long period of time. It could be caused by excessive amounts of current drawn by a motor or appliance, which may be as high as 6 times the rated current. This is caused by too much load on a motor or a circuit. And guys, that's really all you've got to tell me. They just wanted you to tell us what an overload is. But to detect an overload, you would tell me that you would use a clamp meter or ammeter. So if you've got a suspected overload, you put the clamp meter on, and it's just showing what type of meter to use for that overload, right? So that is the second one we can discuss. The third one we can discuss, if you don't work with three-phase much or you don't get one of these faults, is a phase rotation. So you're just going to describe to me how to do a phase rotation test. Well, it's easy. Phase rotation meter, L1, L2, L3, spins clockwise, easy peasy. But a phase rotation fault, you could describe a machine running backwards, a saw running backwards, a fan running backwards, anything three-phase. If you've got the polarity wrong on two of them, and the phase rotation was wrong, it could cause a machine to spin backwards, causing all types of problems. Fans not extracting, saws running backwards, chopping kids in half, etc., etc. Right? So they are the three that we can discuss, we can talk about, and as long as you relay the information I've just given to you, happy days, we're good. Look, fireworks, right? Now then, what's next? The following faults you must show photographic evidence. Now, the biggest thing I get is, oh, Craig, I don't do these types of faults. Make them up. It's fine. Don't worry about it. We're just looking to see that you can find and fix this fault. If you don't come across it naturally, guys, you've got no choice, but you're gonna have to make the fault and then pretend you never made it and find it and fix it as you would normally, right? So let's talk first of all about short circuit and earth fault. Okay, so that's the same criteria, short circuit and earth fault. And I'm just going to tell you really the difference between the two, okay? So a short circuit, sorry guys, it's jumping all over the place. So short circuit and earth fault, right? This slide's in the wrong place, so I'm just going to jump a slide, right? What's the difference between the two? So a short circuit is a line conductor touching a neutral fault. So line, neutral, so line 1, line 2, or line 3 in three-phase, or line 1 in a single phase touching a neutral. That's called a short circuit, right? And an earth fault, it's not an open circuit. It's not a missing earth rod. It's not that. It's a line or a neutral touching a CPC, right? So a line or a neutral, I don't know where them balloons come from, touching the CPC. So a line or a neutral touching the CPC. I'm trying to make that balloon thing happen again. A line or a neutral touching the CPC is called an earth fault. They're both, in effect, a short circuit, but that's kind of how to differentiate between the two terminology types of faults. So first of all, we're looking for you to know what is a short circuit and what is an earth fault and what's the difference between the two. So that's good, right? The test that we're going to be looking for you to do this is an insulation resistance test. And obviously a 0 mega ohms reading, as you can see there, is a bad result. So that's two things are touching. And greater than what the tester can read. My tester reads 500. Yours might read 999, just whatever it is. That's going to be a good result. So that's going to be the bad result you're going to show. Then you're going to show the fault. Then you're going to show the good result. And guys, in these faults, we need a story of the job. But we also need full sequence of safe isolation. Where I put the slide wrong, right? We need the full sequence for safe isolation in the 318 and 317 folder on at least one occasion. Okay, so we need you to be asking permission, knocking off, locking off, warning tag, key in pocket, prove the tester on a known source or a proven unit, test line neutral, line CPC, neutral CPC on a single phase, and do your 10 tests on the 3-phase, and then reprove the tester. Now, I'm not needing you to do all the faults or all safe isolation for every single fault, right? But what I do need you to do is this. For every fault that you show a story of that fault, the board must be locked off. If you're working on a board, it's locked off. If you're working on a circuit, it's locked off. If you don't show me the MCB or the main switch locked off, we can't accept the fault. They make us refuse it. So, even if you don't do it, guys, just make sure you lock that off, right? So that's safe isolation. Okay, the next fault then would be loss of supply. Again, like you guys got to think outside the box. So that, as I've done now today, I've just thought about this. What would I do, right? So loss of supply to me, a blown fuse in a fuse connection unit. Okay, there's voltage, so you use your voltage indicator. There's voltage on the top. There's no voltage on the bottom. You take the fuse out, do a continuity test. No continuity, replace the fuse, put it back in, retest, job done. 10 to 12 pictures from start to finish of that job. Happy days. Yeah, and obviously you can't do safe isolation because you're testing for voltage, but that's simply a loss of supply fault. Then we have got loss of phase or line. This one, guys, is a difficult one. They don't have an open circuit fault in the 2357, so I suggest we do this. We're going to create an open circuit on the line conductors on the ring final circuit. So when you do your end-to-end test on step 1 of the ring final test, you come up with an open circuit. Look, a bad result there, greater than what the tester can read. And then you're going to go around, fix the fault, show the fault broken, so show the lines out. So you've got your loss of line and you're showing it. And then you're going to put them back in and then retest and job done. But let's do a full ring final test on the retest. So step 1, step 2, step 3, including all your calculations. Check out guidance note 3 if you don't understand, or look at my testing video. That would be great. Okay, so that's the loss of line or phase, easy peasy. High resistance joints again. So this is again using a low resistance ohm meter, or as you lot call it, continuity tester. It's a low resistance ohm meter, guys. But you're going to do high resistance joint. So you get a higher than expected reading. Again, if it's on a ring and on the end-to-ends on the line, you've got 0.10, and on the end-to-ends on the neutral, you get 10.86. You know there's something wrong there, so you've got a reading, but it's higher, way higher than the line. You would expect it to be about the same, and it was way higher. Or on a radial circuit, we're going to need to know what your expected result was, guys. So look in guidance note 3 or my testing video, and you will learn how to do a calculation then using guidance note 3, the tables within, to calculate approximate length of a circuit, to calculate how to get your expected result. So any reading you get that's higher than you expect is going to be a high resistance joint. You're going to go around, you're going to find it, you're going to tighten it up, and you're going to show a better reading. And it's as simple as that. Again, 10 to 12 pictures of the story from start to finish. Don't forget your lock off. So that's that, guys. High resistance strength, really straightforward, really simple. And a component fault, you save this one for your observation, guys, because component fault on an observation is so simple. You can cover so much by doing a tiny little fault. My example is a broken socket outlet. So you find the broken socket, so picture or show me on the video, on the live video, the broken socket. You're going to safely isolate. You're going to show the broken socket, replace it with a new one, and then when you've replaced it, switch it back on, do a ZS test, guys, do an RCD test. With the ZS test, we are going to talk like, why do we do a ZS test? What's the expected reading? So let's make a bit of a meat on it. So, table page 145, table B6 for expected results. Why on a result in the on-site guide, why is it different to the regs book? What's the point of that? Why is it the 80% of tableted value? Just give you a clue there. So, an RCD test as per Amendment 2, push button test first. And then times half and times 1 on 0 and on 180, and record the highest on times 1. And you're expecting no more than 300 milliseconds, guys. And that is that. All faults, show board locked off, guys. I reject so much where people working on boards that are not locked off. A main fuse is pulling out. If you pulled out a main fuse, guys, we need your permission from the DNO slip. We need your qualification. You've got to be specially qualified to pull out a main fuse. So we will ask to see the qualification. We will ask to see the permission from the DNO. All right, they will always email a permission. So if you can't provide either of them and you pull the main fuse out, it ain't happening. It's getting rejected. Safe isolation doesn't need to be shown for every fault, but just show it locked off, and make it easy for yourself. No safe isolation using a multifunction test. That's a voltage indicator only. And it's a voltage indicator that complies to GS38. Look at paragraph 19 of GS38, and that'll explain to you why. And each fault, story of fault from start to finish. So 10 to 15 pictures. I put, 8 to 10 pictures, or 8 to 12 pictures, just showing the event of what happened. So we've got full story from start to finish of each fault. And I think that's it, guys. That is 2357 and 1605 fault finding, fully explained. It seems complicated, but as I've just explained to you, I've just used my imagination. I've imagined some scenarios. I've imagined how I would, if I was going into a customer's house, how I would do it, how I would find it, and how I would fix it. I've taken the pictures, the storyboard, and I've just created that fault that way, and that's all they're looking for. Okay, so guys, I hope you found this video interesting. I think it's been really good, and I hope you find it really good too. Leave me some feedback. Of course, as now I'm putting everything on YouTube, so don't forget to like, rate, and subscribe to the channel to get Craig more money when I get more hits and clicks and blah blah blah, and that'll be great for me as well. So thank you very much indeed for your attention.